Hi, and welcome to this first video from the Mechanics course Year 2 on moments. And hopefully moments is an idea that you're probably familiar with from your GCSE physics. But what we're going to do is just go back to the basics and introduce the idea of a moment, and then look at how we solve problems involving moments when forces are perpendicular. So we're going to deal with those top two bullet points in this particular video. And then after that we'll extend it onwards to what happens when the forces are not perpendicular, which is the bit I suspect that will be the extension beyond your physics. So here we go, moments. The moment of a force is a measure of its capacity to turn the body on which it's acting. So if we have a look at this example here with a seesaw, every child who's ever been to a playground, even from a young age, will understand the fact that in order for this seesaw to balance, then the smaller person needs to be further away from the centre than the larger person. Alternatively, we've all done that thing where we've kind of been on the seesaw, stood in the middle, and walked away from the centre of the seesaw, and it's only as you walk away from the seesaw that the thing starts to tip. So the idea that I think every child intuitively understands is that the amount of force you need to get this seesaw to tip is linked to either the size of the objects, the weight of the person, or the distance, how far away from the centre of the seesaw they are. In this case, the centre of the seesaw being the pivot. So what we're going to do is consider clockwise moments or anti-clockwise moments, and if the seesaw is going to be balanced, the clockwise and the anti-clockwise moments need to be the same. So the moment of the force about P is the product of the magnitude of the force and the distance from the point P to the line of action. So essentially that. So the moment about a particular point is force times distance. And this thing is measured in Newton meters. Okay, so let's just have a look at some simple examples of where we can just start thinking about clockwise and anti-clockwise moments. So for this first one, let's start by considering our clockwise moments. So we've clearly got our force here, our 10 Newton force. So we've got force times distance, so it's 10 times 2 is 20 Newton meters. And then the anti-clockwise moments are going to come from this one here is going to make it tip anti-clockwise, and this one here is also going to make it tip anti-clockwise. So it's not necessarily the ones going down cause a certain direction of moment and the ones going up cause a different direction. It depends where they are relative to the pivot. And we can see here that what we've got is a much bigger moment happening in the clockwise direction. So our resultant moment is 7 Newton meters clockwise. So in that particular example, that would cause the rod to tip. Okay, on we go. Let's have a look at the second example. Now, first thing to consider here is this 3 Newton force here. Because it's at the moment, the distance is 0, so that one has got a moment of 0. So let's have a look at what else is going on. We've got clockwise, so the only one going clockwise is this one over here. So that's 2 newtons times by 6, so that gives us 12 Newton meters. And then anti-clockwise, we've got this one here, so that's 4 times 3, which is 12. So as it turns out, we've got a resultant of 0, so that system there is in equilibrium. You'll notice as well, it's like kind of the amount of force required here is less, or half the amount of force that's required here in order for this thing to be balanced. And again, that is entirely to do with the fact that that distance there is double the distance from our pivot to this particular force. Okay, on we go, and let's have a look at the last one. So if we go clockwise on this one, what's happening with the clockwise? Well, we've got this one here. So that's 2 newtons times by the 3 meters. And then we've got the 4 Newton force here, so 4 times 2, so we've got 18 Newton meters going that way. And then resolving it anti-clockwise, we've got the 4 Newton force there, the 2 Newton force there, both of them 1.5 meters away, 9 meters. So in this particular example, we've got a resultant that would be 9 Newton meters clockwise. So again, that one there is not balanced, that would tip in the clockwise direction. Okay, hopefully you're reasonably comfortable and happy with those, and those are ideas that you've seen before, either in your maths or particularly in your physics. So let's now start to make these ideas a little bit more complex, the kind of stuff that you're going to have to deal with on your A-level maths course. So, in the previous slide, I should have mentioned this, kind of the rod was light and uniform, meant it was evenly distributed and it didn't have any mass. What we're going to do now is we're going to put it in a situation where the rod has weight W. And if it's uniform, the mass is evenly spread, so the weight is going to act through the centre of mass in the middle of the rod. So I'm kind of confusing my terminology a little bit there. Weight W, so that's going to be M times G. Right, so according to Newton's third law, if we've got a force downwards that is W, then these two things here, RA and RB, the reaction at A and the reaction at B, have got to be equal to it. So we're not necessarily going to be the same depending on where they're positioned and also depending on the impact of other forces. But in this particular case, if we're just looking at that example there, we've got RA plus RB equals W, which is basically the downward force is equal to the upwards reaction force. And that's a concept that we should be quite happy with by now. So straight away, this introduces an equation with two variables, the reaction force A and the reaction force B. But what we can do is by taking moments about one particular point would allow us to eliminate one of those variables. So if I decide to take moments about A, then I haven't got to worry about the reaction force at A because the moment at A would be 0 based on this. So what I've done now here is, well, let's introduce a couple of distances. So this is the distance that each of these pivots is from the centre of the rod. And then let's have a look. So if we took moments about A, what I've got is a clockwise moment, which would be the weight times by D1. And then the anti-clockwise moment, and we're saying this situation is in equilibrium, so that would be equal to the anti-clockwise moment, and our anti-clockwise moment would be the reaction force times by the distance, which in this case is D1 plus D2. Likewise, if I took moments about B, let's do it the other way around. So moments about B going clockwise, what we've got is the reaction at A times by D1 plus D2, and then anti-clockwise would be weight times by D2. And what you'll notice is this equation here, the variable we've got is RB, the reaction force at B, whereas in this equation here, we've got the reaction force at A. So a careful choice of where to take moments around can help us eliminate bits and pieces and allow us to just isolate the ones we want to deal with. So here we go. Here's an example. We've got a uniform log AB. It's got mass 60 kilograms, and we've got some loads on the log at A and B, and it's held in place by two supports, and you've got all the distances there. So we've got the supports C and D, and we want to find the reaction forces at C and D. So off we go. Let's take first of all our moments about C. So that should leave us just with this one in our equation. Let's see what happens. Let's start off going clockwise. So clockwise, we've got our 50G force times by 3 meters. That's that distance there. And we've got our 60G force times by half a meter, because again, that one there is the weight of the log. So that's the midpoint of our log. And if our log is 5 meters long, then clearly this one here is going to be at 2.5 meters, which means that distance there is 0.5 of a meter. So that's what's going clockwise. And then anti-clockwise, we've got two moments going anti-clockwise. We've got this one here, 30G times by 2 meters. And then you've got the thing that we want, which is RD, again, times by 2 meters. And so what we've got there is an equation in terms of G, just for the reaction force. There we go. Do a bit of solving, and there you go. You've got it. The reaction force at D is 588 newtons. Okay, so that now leaves us to find the reaction force at C, and we've got a choice here. We could do exactly the same thing and do moments about D, or the other option, and I think the simpler one, would be to, let's just consider forces going in the vertical plane. So we've got forces going upwards, so that's RC and RD. Bear in mind we've already got the reaction force at D, and then the forces going downwards. So there we go, nice and simple, and so there's the reaction force at C. Like I say, choice of methods there, and I think kind of that one going with the forces upwards and downwards is probably the easier one of the two. Okay, so let's move on and have a look at a slightly more complex question. And as we tend to find with mechanics questions, we've got a world of information that we need to process and assimilate in some way, and by far the easiest way to do that is to do a diagram. So there we go. There's our beam XY. It's got length 5 meters. We've got supports that are 1 meter away from each end. We've got the distance, so we've got Harry standing on here, and we're going to say let's make it the distance from Y for Harry be X, and therefore Kath, our other child, is going to be 2X. What else have we got in here that we haven't considered yet? We've got reactions at P, reaction at Q, which is 3 times it, and then the final thing we've got is the weight, which is 600 newtons, that it's on a uniform rod. So it says modelling the beam as uniform. So there we go. there's our diagram. So you might want to just kind of take a second just to have a reread of the question and have a look at the diagram and make sure you're happy with all of that. And if you are, let's crack on. And so let's start off by thinking about forces upwards and downwards. So there's our basic. Then straight away, that's kind of nice and simple, and that's going to allow us to work out the reaction force at each point P and Q. So we know the reaction force at P from that is going to be 375, which means the reaction force at Q is 1125. So there's a good start. So we've found two of our variables already. Now, bearing in mind we've defined everything about y, it makes sense to take moments about the point y. We could have chosen points about y, x, q, p, but let's deal with y here. So what have we got? Let's go clockwise to begin with. So clockwise we've got rp times 4 plus rq times 1, and then going anti-clockwise, that's going to be the weight of the children and the weight of the beam. So there we go. There's Kath, 450 times 2x. There's Harry, 450 times x. And there's the moment as a result of the weight of the beam. And we've got our P, we've got our Q, so that just leaves us with an equation in terms of x. And there you go. As it turns out, Harry is 83 centimetres from y. Now, it's worth mentioning here as well that when we did the diagram, technically speaking, I put Harry here, but it could have been, let's say he could have moved and he could have been in between Q and Y. We didn't know precisely where he was going to be. And if we'd have taken moments about Q, that would have created a problem. But by taking moments about Y, that gets rid of the fact that we don't know where precisely he was. Because let's say if we'd have taken moments about Q, would Harry's moment have been clockwise or anti-clockwise? Well, at that point in time, we just didn't know. But let's say by taking moments about Y, that gets around that particular issue. Okay. Moving on, so let's have an exam question. So again, we've got a load of information, so let's turn that into a diagram. There it is. So we've got a couple of strings supporting our rod. So we've got tension in the string at A, we've got tension in the string at B, and those two things are different. We've got a uniform rod, so it's got mass 12 kilograms, and we've got a load of 8 kilograms attached at that point there. So it says, first of all, find the tension in the rope at B. So we don't know either tension. They weren't linked together as we were in the previous example, but if we're interested in the tension at B, let's take moments about A, so then we haven't got to worry about that, and we'll create an equation where we've got tension at B as being part of that equation. So let's take moments about A. So here we go. Here we go again, clockwise. So we've got the 0.8 times 8g, we've got the 1.2 times by 12g, and then going anti-clockwise, we've got 2.4 times by the tension at B, and again, now we've just got an equation in terms of the tension at B, so we can solve that, and we know our tension there is 84.9 newtons. That's part A sorted. So let's move on and have a look now at part B. So things have changed somewhat. So it says the plank is now modelled as a non-uniform rod, and that's caused a change in the tension. So the tension at A is 10 newtons more than the tension at B, and we need to find the distance of the centre of mass from A. So here we go again, diagram coming, because things have changed, and that's what we're now looking at. So we've got the tension at B, I've called it T, and the tension at A I've defined in terms of that, so it's just 10 more than the tension at B, so that's T plus 10. And we've still got our mass that's been placed on this rod at the point C. That hasn't changed, but what we've got now is a change in the distance of the centre of mass. So again, as with the example with the two kids on the rod, I've just called that distance x. So let's have a look at what's going on. So we've got our resolving forces going upwards. That's going to provide us with the values for the tension. And so our tension is at B is 93 newtons, which means at A it's going to be 103. But we're not going to worry too much about that because we've already used that value to get the tension here. And what I'm going to do is now take moments about A. And again, clockwise, here we go. So we've got the 8g times by the 0.8 plus the 12g times by x. And that's going to equal the anti-clockwise moment, which is going to be the 2.4 times by 93. And there you can see now an equation we've just got to solve in terms of x. So that leads us to x equals 1.36 meters. And that's that bit done and sorted.